So let's do some tangent slopes on parametric equations. So we start off with a very innocent looking curve. Here we got x equals t plus 1, y equals t squared. I went ahead and I graphed it, and we're asking, can we find the tangent slope at t equals 1.75? When t is equal to 1.75, x is equal to 2.75. So I know that's somewhere around here. And what we're looking for is the slope. That's what we want, the slope around there when t is equal to 1.75. Alright, this translates into, can we find dy dx at that point? The trick is to do this dy over dt all over dx dt. You see, we treat these differential quantities almost like algebraic quantities, which is amazing on its own because they're very close to zero. It's almost like dividing by zero, and we don't care. We just divided both top and bottom by something that's really close to zero. It's amazing that we can do that, but we can. If you multiply both sides by this, you see this would be a variation of the chain rule that you learned in a previous semester calculus course. Anyways, that's the whole trick. Now I've got to get the differential dy dt. I could look at the yt relationship. To get the dx dt, I would look at the xt equation. And so for the top, I'm going to look at here. This one says that y is equal to t squared. So I could slap a d on both sides. I slap a d on that side. I slap a d on that side. And I get that dy is equal to 2t dt, or said differently, that dy dt is equal to 2t. Duh. So this becomes 2t. Now for the dx, I have x is equal to t plus 1. Do d dt on both sides, so dx dt is equal to 1. That's equal to 1. Now I have that dy dx is equal to 2t. Now I need to evaluate that at t is equal to 1.75. So the solution would be that dy dx at t is equal to 1.75 is equal to 2 times 1.75. And that's it. So the slope is roughly, let's see, 2.5, 1.5, that would be 3.5. That's the tangent slope here. Rise over run is 3.5. Easy, right? That wasn't so bad. The key here was this dy dt business up here. That's the whole key. Alright, let's try that again. One more problem. Let's clear the screen here and see if we can do that one more time. Maybe change it up a little. How about we do some tangent slopes on ellipses? Check this out. At 45 degrees, that would be somewhere around here. 45 degrees, that's that point right there. 45 degrees. At 45 degrees, can I figure out the tangent slope? So I'm looking for, well, that's not very liney. That's not either. Alright, last try. That's it, that's all you get. Alright, so we find the tangent slope there, and so what we want is dy dt. We observe the trick is to write it under dt. X dt, and that would be equal to get dy dt, I look at the yt relationship. Dy dt would be equal to 2 times cosine t. So that's what goes on top, 2 times a cosine t. To look at the dx dt differential, I would look at this relationship and I get that dx dt is equal to negative 5 sine t. That would be negative 5 sine t. And now we're doing this at 45 degrees. So that would be equal to, that would tell you that dy dt, let's keep these things separate, at t is equal to 45 degrees is equal to 2 times cosine of 45 degrees all over negative 5 times sine of 45 degrees. Whoops. And you could figure that out, whatever. I think actually these are the same for cosine. They match at 45 degrees, and so you get the answer is 2 over negative 5. Okay, so you rise 2, you go up left 5, you go rise 2, you go left 5. We did it. We found the tangent slope at 45 degrees. And it wasn't even that bad. Easy. Right? Calculus on parametric equations. Alright, we should clear the screen here and see what we should do some more calculus on these. How about finding the area under the curve? How does that sound? Can we do area under the curve with t's, with a parameter, with parametric equations? I'm not afraid. Come back, we'll do so.